Welcome to lecture 1.12. We'll continue with what we were doing on the previous turn. We had taken up this example and we were trying to simplify this system and convert it into a single transfer function. So what we had done in lecture 1.11 was to actually take this this summing junction that we have, this pick-off point that we have here, of this V3S, and take it past the block G2. So we had just moved this pick-off point from here and we had moved it past G2. We had taken up the signal from here, and once we had done that, we had consequently, because we were now picking up a signal which was G2 times V3, we had divided it by G2. So we were picking up from actually this point. We were picking up from this point. Let me first rub this off. So instead of this signal being picked up from here, we were picking up from this point, dividing by G2, and then feeding it into the summing junction. And then we had combined this G2 and this gain of 1 here to come up with a single block instead of the two blocks. So let me draw what we had done actually. Finally, what we got as a result was something like this. So we had this RS, we had the G1S, right, and then we had this G2S. We also have this summing junction here, right, with a plus sign here and a minus sign here. We have this H2S here, right, and we had actually then picked up since we had picked up the signal from instead of here, we had picked it up from here, so we were actually getting 1 plus 1 by G2S at this point, and we were then continuing this, adding it to the summing junction that we have here. Then you have this G3S, CS, H3S, right, and you also have this another feedback loop here, which is your H1S. So the signals are the same. You have RS at the input, CS at the output. This is your V1S here. You're still getting V2S out here, which you're feeding. You're still getting V3S, but you're not tapping V3S. You're tapping V4S, right? And then you're taking this V4S and you're multiplying it with 1 and with 1 by G2S to get your V3S, and then adding it and giving it as an input to this summing junction here as a single input. And this V8S remains the same, V5S here remains the same, right? So everything else is similar. At the output of the summing junction you have V5S. Yes, okay. So now once you have done this change, you can now further simplify this. You can simplify this part. You can simplify this part by treating it as a feedback loop. So this whole thing in green will be replaced by G2S divided by 1 plus G2S H2S, right? And then you have this 1 plus 1 by G2S here, and this whole thing here can also be replaced by G3s divided by 1 plus G3H3, right? So this is your CS output, G3s H3s. And what is left now is your G1s here, this is your G1s here, right? And also this feedback that you're taking, this feedback V4 that you're taking from here, because you're taking this feedback from this point here just before it enters 1 plus G2s. So this feedback path, this one more feedback path is still left, right? So this is your H1s. Now you can further simplify this. These two are in cascade, and then this is in the feedback path for the two. So I'll drop the bracketed s in order to make it look simpler. So what I get in the forward path here is G1 G2 divided by 1 plus G2 H2, and then I have a feedback loop with H1, right, in the feedback path. So I have to, if this whole thing I have to replace by a single transfer function, I'll write this is the forward path, G1 G2 1 plus G2 H2, right? And in the reverse path you have H1. So this is G divided by 1 plus GH. 1 plus GH would be G1 G2 H1, 1 plus G2 H2. So this whole block, this whole thing in black here gets replaced by this block, and this is your RS here. And then you have these two blocks which are again in cascade, and which you can simplify. You can write this as G2 into 1 plus G3H3, and in the numerator you have 1 plus G2 into G3, and this is your CS, right? You can further simplify this. The first block here can be simplified, G1 G2 divided by 1 plus G2 H2 plus G1 G2 H1, right? So I'm multiplying and divided by 1 plus G2 H2. So I get 1 G1 G2 in the numerator, 1 plus G2 H2 plus G1 G2, 1 plus G2 H2 plus G1 G2 H1. So this is this block. This block gets multiplied. This the other block in cascade is 1 plus G2 into G3 divided by, this is not required, divided by G2 into 1 plus G3 H3. So this is your RS, the input, and this is your CS, the output. And let us see if these two in cascade, with these two in cascade you can multiply, and these two will cancel out. G2 will cancel out. And do you have anything else that it cancels out? No, I don't think anything else can be cancelled out. So CS by RS would be given by G1 G3 1 plus G2, right, divided by 1 plus G2 H2 plus G1 G2 H1 into 1 plus G3 H3. So this is the final transfer function. Let me check whether what we have done is correct. Okay, 1 G1 G3 1 plus G2 1 plus G3 H3 into 1 plus G2 H2 plus G1 G2 H1 here. So this is the transfer function. You'll have to write down s as a function of s if you have to be correct technically, but in case there is shortage of time or anything, then you can quickly write down in terms of g and h. So I hope this reduction of multiple subsystem systems by block diagram reduction is clear. Now we come to another method by which we do the same thing. We simplify multiple subsystem systems, and that method is called the method of signal flow graphs. So instead of drawing the block diagram, we draw the signal flow graph for a particular process, right, in which we have multiple systems. So when you draw a signal flow graph, you basically represent a system like a branch. So this is your system, and you represent, so your system is would be represented like a branch, and your signal would be represented like a node. So this is again a representation, just like you have a block diagram representation. In a similar way, you have this representation. So a system would be represented like a branch, and a signal would be represented like a node. So what happens is the because of this is a slight, there is a difference in the way in which we draw the block diagram and then solve it, and the way we draw signal flow graphs and then try to solve them. So basically, if you have something like this RS, GS, CS that you have seen before, where RS is the input, CS is the output, and GS is the system. If you have to draw the same thing using signal flow graph, you'll draw because there are two signals, you'll draw two nodes, RS and CS, right? And then you have this this is normally written on top. So you have this GS written on top, and the signal is written at the bottom. So in case you have a cascaded system in which you have a number of these blocks put together, right? So you have G1s, G2s, G3s, if you have something like this, and then you have these signals RS, CS is the output, and then you have these intermediate signals X1s, X2s. Then you'll draw something like this. So first draw your nodes. So RS is a node, X1, X2. See, these are the four signals. So we write down the signals RS, X1s, X2s, CS, and then we draw the branches, which are the systems that we have, right? So this is our G1s, this is our G2s, and this is a G3s. What about a feedback loop, like say for example something like this? GS, you have a summing junction. The advantage of this is that you don't need to draw summing junctions in this. The need for that is avoided. So you'll see how. So you have RS here, and then you have this error signal that comes in here, and then you have this output signal that you're getting here. How would you draw this? So let us first draw the signals. So this is my RS as a node, then the second signal is ES as a node, and the third signal that I have is CS as a node. So between ES and CS, I have this transfer function, I have this system GS, and between this CS node and the ES node, right, I have this minus HS. So just sorry, just rub this off inadvertently. So I multiply the signal CS with minus HS, right? With minus HS, and then I get the signal ES, isn't it? Because uh, CS into minus HS, and when you add this RS, so the gain here is 1. So RS minus CS HS gives me ES. So basically, the what are the principles that we are actually following? The principles that we are actually following while we draw the signal flow graph would be clear when we define what are the parts of the signal flow graph. So the first part of the signal flow graph is the node, right, which represents the signal. So it represents the system variable, which you call the signal, right, or signal, which is equal to the sum of all incoming signals to the node, equal to the sum of all incoming signals to the node. What does this mean? It means that when you drive this something like this and you wrote ES here, so it automatically means that ES, the system variable here, is equal to the sum of all incoming signals. And what are the incoming signals? The incoming signals are 1 RS into 1. So RS into 1 is the incoming signal, and the other incoming signal is CS into HS with a minus sign, right? So ES is RS minus CS HS, and this is actually what you have done in the block diagram. Although it is clearer from the block diagram, less clear from the signal flow graph, but this is the advantage of the signal flow graph, that the requirement for drawing the summing junction is not there. Okay, so we have to remember that node represents a system variable or signal which is equal to the sum of all incoming signals to the node. And another important thing is that all outgoing signals from the node are equal to the node variable, so that will basically represent your pick-off point. So if you have a signal ES and you are taking this signal and you're basically multiplying it with G1s, G2s, G3s, then basically you are getting X1s, you're getting the signal X1s, the node variable X1s here, the node variable X2s here, and the node variable X3s here. It means that X1s is equal to ES into G1s, right? X2s is equal to ES into G2s, and X3s is equal to ES into G3s. So all the signal ES, when you pick it up and you multiply it with different the different gains or different transfer functions, you can basically all outgoing signals from this node are equal to the node variable, so it does not get divided actually. So which essentially means that if you have something like a parallel combination, which you did earlier, in which you had this you had these three blocks, you had a pick-off point, so you had a signal ES here, and you had a pick-off point G1, G2s, G3s, and you were adding all the three up, say for example using a summing junction here, so we're adding all the three up and you're getting something else, say ys here, then you can represent the same using this structure that you have drawn by now creating another node here, right? This node you call ys, right? And then say your ys is the sum of all the three signals, so you just connect these like this, and the gains are 1 here, 1. So this is the signal flow representation for the parallel configuration. These are your x1, x2 and x3. So and this is the convention that you are following, that all incoming signals, that the value of the node variable is equal to the sum of all incoming signals to the node. So what are the three incoming signals? X1s, x2s, x3s into 1. Each of them is multiplied with 1, and that is equal to y of s, right? So this is how we would write. Please remember this is important. Then you define, this is the definition of node. The other definition is that of branch. Your branch is a signal traverses along a branch from one node to another in the direction indicated by the branch arrow. So a signal will traverse or will travel along a branch from one node to another in the direction indicated by the branch arrow, and in the process it gets multiplied by the gain of the branch. So this is clear. This is not very difficult to understand, right? Then you also define something called input node or source nodes. So this would be a node which has only outgoing branches. So a node which has node with only outgoing branches. In a similar way, you can define something called sink or your output node, right, which has only incoming branches, right? Then you define path. So there is something called path, right? In this we need these definitions because we'll require them to find out the formula for simplifying a signal flow graph. So the definition of the path is this: traversal of connected branches in the direction of the branch arrows. So you move along the branch arrows, you are moving along the path, right? But the condition is that such that you're not moving around in circles, such that no node is traversed more than once. So you have to, a path would be one which will not contain a closed loop, right? More than once. Very simple. So for example, in this case, if we have this is a path, right? This is a path. This cannot be a path like this because you're not traversing in the direction of the branch. But yes, this would be an independent path. This one, oh sorry, This one would be an independent. This one would be an independent path, this one, right? This is an independent path. So this is a forward path, right? And this is a reverse path. So there are two paths in this. So this is the definition of the path. And then you have forward path. So a forward path would be a path from source to sink, right? Path which takes you from source to sink, right? It could be one or it could be many. There could be many paths from source to sink. For example, in this case, this is your source and this is your sink, and you have these forward paths. This is one forward path, this is another forward path, this is another forward. There are three forward paths. So paths from source to sink. Then you have loop. You define path which originates and terminates at the same node. A path that originates and terminates at the same node, right? At the same node is called a loop. Now look at this. We have a loop here. Yes, we have a loop here. A very good example of a loop is this. See, so this, you start from this point and you can traverse you have to traverse in the direction of the arrow, because that is the definition of the path, and then you come back to the same point. So you have a loop here. Yes, but you don't have you cannot have a loop in this. You cannot go like this and come back like this, because you would not be traversing in the direction of the arrow. So there is no loop in this, but there is a loop in this, right? Because loop is a path that originates and terminates at the same node, right? So you have to traverse in the direction of the branch, right? Then you have another thing which is called the non-touching loop. Right? NTL for short. Non-touching loop. Any loops that don't have any node in common. They don't touch, right? It's very simple. Any node in common, they are said to be non-touching loops, right? Then you have another important thing which is called forward path gain. Forward path gain is the product of the branch gain encountered in traversing the forward path. So as you move in the forward path, what is the gain that you encounter? So in this case, you encounter a gain of G1. So this is the forward path gain. In this case, you encounter a gain of G2. So in this forward path, you encounter a forward path gain of G2. In this forward path, you encounter a path gain of G, right? So this is called the forward path gain. In a similar way, you have something called the loop gain, which is again the gain that is product of the gain that is encountered in traversing a loop. So when you move in a loop, what is the gain in terms of what are the systems that you are actually encountering, and what is the product? So when you move like this, let me draw this with a different color. When you move like this in the loop here, so you start with a gain of GS and then you multiply it with HS. So minus GS HS would be the loop gain of this loop here, right? So this is the loop gain. So these definitions are important because we want to derive a formula on the basis of the signal flow graph that we'll be plotting, which will give us the transfer function for the system which we are trying to simplify. So more discussion about that formula and about converting from block diagram to signal flow graphs in the next lecture. Thank you very much.